Hi everyone, in this video we can discuss about various binary adder circuits and its implementation. We have a varieties of such binary adder circuits, and for our lab section we can discuss four such binary adder circuits. They are half adder, full adder, half subtractor and full subtractor circuit. So before moving to that circuit implementation session, we can just understand some basics about the binary number system. We all are familiar with our decimal numbers, right? So in our decimal numbers, in a decimal number system, we have 10 different symbols like 0, 1, 2 up to 9. 10 different symbols are available. Using these 10 symbols, we can generate any decimal numbers. Similarly, we are going to discuss about binary numbers. We are dealing with binary numbers now. So in a binary number system, which is a number system with base 2. Base 2 means we have two different symbols here. One is 0 and the other one is 1. Okay, exactly like our decimal system. Here it is base 2 system. So it contains two different symbols. They are 0 and 1. Okay, using the 0 and 1, we can generate different binary numbers. So suppose you are allowed to use only one bit. Okay, you can make use one bit. Then how many numbers we can generate? How many binary numbers we can generate? Only two. One is 0, other one is 1. So we can consider this 0 as equivalent to decimal 0 and this is equivalent to decimal 1. And suppose you are allowed to use 2 bits at a time. Okay, you are allowed to use 2 bits at a time. In that situation, how many binary patterns you can generate? We can generate 4 different patterns like 0, 0, 0, 1, 1, 0 and 1, 1. So we can consider this 0, 0 as equivalent to decimal 0, 0, 1 as decimal 1, 1, 0 is equivalent to decimal 2, 1, 1 is equivalent to decimal 3. And suppose you are given or you are allowed to use 3 different 3 bits at a time. Okay, you can make use 3 bits at a time. Then how many binary numbers you can generate? How many different binary patterns you can generate here? Using these 3 bits, we can generate these 8 different binary patterns. The first one we can consider it as 0, which is equivalent to decimal 0. Next one does equivalent to decimal 1, decimal 2 and so on up to decimal 7. That means using 3 bits in binary number system, we can generate 8 different unique patterns. These 8 patterns are equivalent to our decimal numbers from 0 to 7. Okay, so suppose you are allowed to use 4 bits at a time. In that case, in the binary number system, how many different unique patterns you can generate? Here it is base 2, that is 2 to the power number of bits, 2 to the power 4. Total 2 to the power 4 is 16. You can generate 16 different unique patterns. They are equivalent to the decimal numbers from 0 to 50. This is our normal rule for generating different binary numbers. Here it is 2-bit representation. How many patterns are possible? 2-bit representation. Then we can consider the base 2 with the power number of bits. Here it is 2-bit. Right? Then total 2 to the power 2. 4 different patterns are possible. These 4 numbers are ranging from 0 to 3. Okay, and this is that normal rule for generating our binary numbers with different number of bits. So using the 4-bit, we have already seen we can generate 2 to the power 4 different possible values. 2 to the power 4 means what? This is possible. We can generate 16 different values. And these values are ranging from 0 to 15. These 16 patterns we can map with the values, the decimal values from 0 to 50. just like that. Okay, so these are all about the binary numbers. Now we can consider that half adder circuit implementation. So half adder is a circuit in which we can provide two inputs, 2-bit input. One bit as A, second bit as B, and it will generate two outputs. One is the sum value and the other one is the carry value. This is the half adder circuit. This is the logical representation. Okay, so what is the meaning of this? It is clear that here we are going to make use 2 bits as inputs. So using 2 bits, how many patterns are possible? 4 different patterns. What are they? 0, 0, 0, 1, 1, 0 and 1, 1. These are actually equivalent to our decimal numbers from 0 to 3. Okay, so here it is considering this half adder circuit perform adding of 2 different bits. Okay, one is A, this is like A plus B, adding 2 different bits. Okay, so first case it is 0, 0. So by adding 0, 0, this is A, this is B. Okay, this is A, this is B. 0 plus 0 is 0. Is it generate any carry value here? No, 0 plus 0 is 0. It will not generate any carry to the next level. So the result will be like this. After adding these 2 bits, it will generate the sum value 0 and it will not generate any carry to next level. So the carry out is 0 here. Okay, next case 0 plus 1. What is the meaning in that? Suppose here it is A is 0, B is 1. So while adding these 2 bits, 0 plus 1, we know that 0 plus 1 is 1. And is there any carry here in this addition? No, it will not generate any carry to the next level. Okay, so the sum value is 1 and the carry out is 0. And the next case, that is 1, 0. A is 1, B is 0. So adding these two, it will generate some value 1 plus 0 is 1 only. And again, it will not generate any carry value to the next. Okay, so the sum is 1. The sum value is 1 and carry is 0. Carry out is 0 here. And the last case is 1 plus 1. That 1 plus 1 is actually what in decimal? 1 plus 1 it is 2. Is there any direct representation for 2 in this case using this 2-bit pattern? Yes. This is equivalent to our decimal 0 and this is equivalent to our decimal 1. This is equivalent to decimal 2 and this is equivalent to 3. Okay, so 1 plus 1 is actually what? 2. In 2 in binary it is actually 1, 0. Okay, what is the meaning in this addition? 1 plus 1 is 2. 2 in binary it is 1, 0. This 0 comes under this sum part and the remaining 1 is shifted as a carry out to next level. Here it is carry out to next level. So in this case 0 is the sum and this 1 is the carry out. So that is represented here, the 0 and 1. Okay, so this is the case of our half adder addition. So for this we need to generate the circuit for the sum portion and carry out portion. Okay, so consider this truth table and the sum part. Here it is, the sum part. Okay, here it is, the sum part. And here that 1. This 1 in that result sum part for the corresponding AB pattern is 0, 1. That is A bar B. And one more combination is there. For this input pattern 1, 0, the output is 1. That is A B bar. So this is the expression for our half adder sum. What is this actually? We know that A bar B or A B bar is actually A XOR B. This is that XOR gate operation. A bar B or A B bar is equivalent to XOR operation. Okay, and what about the carry? What is that Boolean expression corresponding to this carry out? Here only this particular row, the carry out become 1. And this is equivalent to, this carry out equal to 1 comes for which binary pattern, input pattern? It is A equal to 1 and B equal to 1. And all the other three cases, the output is carry out is 0. Okay, and here for this particular sum column, that sum equal to 1 for these two input cases, that is A bar B or A B bar. And here it is the carry out equal to 1 only for this particular row, that is for A equal to 1 and B equal to 1. So this is that Boolean expression for carry out. Okay, so how can we implement that circuit corresponding to this half adder sum and carry together? This is like this. This is equivalent to A XOR B. So take two input A and B, which is taken as an input to our XOR gate, and thus generate the sum. And similarly for the carry, we need to take one AND gate. The carry out is actually A and B. This is very simple circuit if XOR gate is available to you. Suppose the question will be like this. Implement this half adder circuit using basic gates only. Basic gates are AND gate, OR gate and NOT gate. AND gate, OR gate and NOT gate. These are the basic gates. And suppose the question is for implementing your half adder circuit using this basic gates. In that case, we need to make use this particular expression directly for implementing some part, and this is for implementing carry, because here we have no such XOR gate, because XOR is not a basic gate. We can make use AND gate, OR gate and NOT gate only for this kind of implementation. So this is the circuit that perform as the half adder, and here it is here we are using NOT gate, AND gate and OR gates only. So you need to practice, or you need to mark this circuit exactly like this. Then it will be easy for you to connect this kind of complex circuit without making any error. That means you need to mark this gate with the IC number properly. And also you need to mark that input output port of your ICs properly in this diagram. After marking all these input output ports and ICs in this diagram, then start the connection. Then it will be easy for you to complete or finish this circuit without making any further mistakes. Okay, so always practice like this. Draw the circuit in your notebook, then mark the IC number properly, then also refer this pin diagram of different ICs and mark this number. This is our NOT gate, and we can refer this one. We can take first A input and connect with the first pin of our NOT gate. So mark here 1 for IC 7404, and 2 will be the corresponding output. So mark 2 for this output port. Okay, so these two are used here. And for next one, take an external input as B, which is connected to the third pin of our NOT gate again, that 7404 IC, that is this one. Take this as the output. This is 4. This is actually what? This is B bar and this is A bar now. This spot indicate A bar, it will generate B bar. Now we need to perform what? The first expression is A bar B. So use an AND gate, mark that IC number and take that 2 port of NOT gate as an input to our first input of AND gate, and this B as the second input of our AND gate. So refer our AND gate pin diagram and connect these 2 ports. And this is our A bar B. Okay, so mark it as 3. Next, here it will be A B bar. So take the A and connect with the 4th pin of AND IC, and this is B bar is connected as 5th input of our 7408 IC. This one. Corresponding to this input, 6th is the output. Okay. So mark this as the 6th one. We need to perform OR operation. So take one OR gate again and take this 3 out and 5 out of our 7408 IC as the 2 input of our 7432 IC. That is the 2 input OR gate. Okay. Then this will be our final sum output, A bar B or AB bar. Okay. So you have to practice always like this. Draw the diagram neatly in your notebook, then mark the IC numbers properly and refer the pin diagram and mark input output port like this. Then it will be very easy for you to implement any complex circuit without making any mistakes. Okay, so and this is the part for our carry out. Carry out expression is actually A and B. So take the same A and B input, connect with 9 and 10 input of our AND gate, and this will be our corresponding final carry out output. Okay, so connect this to the external output. Again, connect this 3rd pin of our OR IC to the external output. And you need to verify this truth table. For 0, 0, the output will be like sum 0 and carry out 0. And for the input pattern 0, 1, output would be this 1, 0. And for 1, 0, it will be 1, 0 and 1, 1. It is 0. Okay, so this is about half adder circuit implementation using basic gates only. And you need to follow the same procedure for such logic gate based circuit implementation. Next is about our full adder circuit implementation. Full adder means here we need to consider 3 different inputs and it will generate 2 outputs, and these are external A and B input, and the 3rd one indicate carry input, and it will generate 2 output, one as the sum and other as the carry out. So this is our real scenario. Suppose consider the decimal system again. In decimal system, in usually we can add 2 digits at a time, just like this. This operation is like our half adder binary addition. Okay, but in our real situation, sometimes we need to add like this. Okay, or someone. Numbers should not always be like a single digit. Numbers will be a sequence of different digits. This will be our real scenario. We need to solve this one also, this kind of situation also. In that case, we need to consider, here it is the decimal system, base 10 system, right? So while adding 8 and 3, we will get a value 11. So in that 11, in decimal, 11 is represented like this. This one will comes in this what? Sum part, and this MSB1 will transfer to next level as carry. Then for the next level addition, we need to consider these three symbols together. 7 plus this carry in value 1 plus 6. Then it will be 14. 7 plus 1, 8. 8 plus 6, 14. 14 in decimal it is 14. Write this LSB4 as a part of our sum and take this 1 as a carry to next level. Now here we have three symbols to add. Right? 1 plus 1 plus 2. Then it is 4. Here it will not generate any carry further to the next level. So this is 4. We can write the 0 here. No need of that because it is 0 in the MSB position. We can simply neglect that 0. If it is in this MSB position, then we can neglect. So the result is 4, 4, 1 here. We need to follow the same procedure in order to perform addition in binary system also. Suppose our number is like this. This is a sequence of binary bits. We need to add this with another binary number like this. And we need to start this addition from the LSB and we can move towards MSB like this. Exactly like the addition in our decimal system. Same rule. There is no difference in that procedure. Instead of 10 different symbols, here we are considering only 2 symbols. That is the only one difference. And the rules of addition is the same. Here 0 plus 1, it is 1. And it will not generate 0 plus 1 is 1. It will not generate any carry to next level. There is no carry here. Next, no carry means carry is 0. Okay, so here we need to add 3 bit and the carry here it is 0 because there is no carry from the previous level of addition. So it is 0 plus 1 plus 1. It is actually 1 plus 1 is decimal 2. Decimal 2 in binary it is 1 0. Right. So we can write this 0 here and pass this 1 as a carry to next level. Right. Then here we need to add. Here the carry is 1. Carry in is 1. This particular input is 1 here. In the previous case this carry input is 0. Here it is 1. So add 1 plus 0 plus 0. That is 1. 1 in binary is 1 itself. Without that 1 can be write like this or write like this also 0 1. This simply write this 1 or 0 1. Okay. In this case write the 1 here and pass this 0 as a carry into the next level. Okay. So then add 0 plus 1. Here it is blank. So 0 plus 1 is 1. It will not generate any carry to next level. Okay. So this is our final result. So in such situation, if such carry will generate in the previous level of addition, we need to consider the carry input for the addition of our next level. Okay. So in order to perform this kind of real addition application, we need to make use this full adders. 2 inputs along with we need to consider the carry value coming from previous level of addition. And after this full adder operation, it will generate a sum value as well as some carry out value. It will be the carry in of our next level. Sometimes this carry out will be 0 and sometimes it will be 1. This will form the carry input of our next level of addition. Total, we need to consider 3 different inputs here. And in the first level of addition, see this? In all the cases, all such binary addition, the first level, the C input will always be what? It will always be 0. This is just the starting stage of our addition, that LSB level. least bit level. Here the carry input always be equal to 0. And based on this level of addition, it will generate a carry out to next level. That carry out will form the carry input of our next level of addition. Sometimes that carry input will be 0 based on this level of addition. Sometimes it will be 0 based on this level of the result generated after this level of addition. So this is the principle of our full adder addition. Okay, so this is this truth table generated for this full adder. Okay, so we need to consider A, B and C input, and it will generate two output, the sum and carry out. Okay, so consider this one. 0, 0, 0 means if both the inputs are 0 along with the C in equal to 0, that is A equal to 0, B equal to 0, C in equal to 0, it will generate what? 0, 0, 0 addition. It will generate 0 plus 0 plus 0 is 0 and no carry out. That means sum equal to 0, carry equal to 0. And what about this 0 plus 0 plus 1? 0 plus 0 plus 1. That is sum equal to 1 with no carry. That is sum part equal to 1, carry is 0. Similarly here also 0 plus 1 plus 0, sum equal to 1, no carry. And what about this one? 0 plus 1 plus 1. 0 plus 1 plus 1. In this case, 0 plus 1 plus 1. 1 plus 1 is actually 2. In binary, the 2 can be represented using 2 bit like this, 1 0. Okay, so this least 0 comes as a part of our result and 1 is transferred as a carry out to the next level. Okay, so the sum part is 0, carry is 1. And here again it is 1 plus 0 is 1 with no carry 0. And this one, 1 plus 0 plus 1, the same. 1 plus 0 plus 1 is actually 2 in decimal. 2, that binary equivalent of 2 is 1 0. This 0 comes under sum and this comes under carry. For this case, 0 and 1. The same, 1 1 0. The sum is after adding this 1 plus 1, it is 2. 2 in binary is 1 0. The 0 comes under sum part and this 1 comes under carry. And what about the last case? 1 1 1. So while adding these three, 1 plus 1 plus 1 is actually 3. In binary system, using minimum number of bits, the 3 can be represented like this, 1 1. So this one comes under sum part and this one comes under this carry. That is this entry. Okay, so based on this, we can write the Boolean expression corresponding to this sum and carry. Okay, this is the expression corresponding to our sum. Consider this particular column, sum column, and here it is 1, here it is 1, here it is 1, here it is 1. And what are this input combination corresponding to this sum equal to 1 rows? Here it is A bar B bar C in. This is A bar B C in. Sorry, A bar B C in bar, A B bar C bar, A B C. Okay. The C in is written here as C. And we can make use CAMAP method, or we can make use that Boolean laws and postulates for simplifying such expression. Okay, so we can make use that Boolean law and the expression will be like this: A XOR B XOR C. So for the full adder circuit, the sum is equivalent to A XOR B XOR C. We can make use that K-map method of simplification, or we can follow with the Boolean laws and postulate for simplifying such expression. And after simplifying, it is equivalent to A XOR B XOR C. Okay, and the carry part. This is the K-map based simplification. We can discuss about this K-map based simplification later. And what about this carry out expression? So here it is 1, here it is 1, here and here. Corresponding to 1, this is A bar B C in. Here it is A B bar C in. Here it is A B C bar. Here it is A B C. And after simplifying this, the expression will be A and C or B and C or AB. We can follow the same with Boolean postulates. Okay, we can discuss about this K-map based simplification later. We can try this with Boolean postulates now. For this corresponding one, that input combination is A bar B C. Sorry, A bar B C. A bar B C. Next, it is A B bar C. A B bar C. We can write this A B bar C. Next, A B C bar. A B C bar. Last one is A B C. Okay, in order to simplify this, we can repeat this particular term 3 times. That is A B C 3 times. Suppose in an expression, suppose one term appears 2 times, we can reduce it into 1. Here we have implemented the reverse. This term is there. For the here it is already there, this term. Now it is repeated 2 more times for that simplification purpose. Okay. Now we can combine these two. And which one is common? A and B is common, and rewrite this as AB C bar plus C. Then it will be equal to AB. This is equal to 1. Okay, then combine this term with this term. Which one is common? AC is common, right? Then we can write this as AC and B bar plus B. That is equal to AC. And consider the last term, this one with this. Then which one is common? That BC is common, right? Then BC, A bar and A. That is equivalent to BC. Now we can write this as simplified form AB or BC or AC. Okay, this is that simplified expression which is easily available using this K-map based simplification. Okay, so this is the expression for full adder carry out expression, and sum is AX or BX or C. Suppose if the question is for implementing a full adder using any gates, then we can easily implement using XOR gate, AX or BX or C. For that we can make use 2 different XOR gate, 2 input XOR gate and generate circuit. But sometimes the question is for implementing full adder circuit using basic gates only. Then there is no option for using these XOR gates. We need to make use AND, OR and NOT gate. So this is that circuit. Okay, so just like our previous half adder circuit, we need to mark, after drawing this diagram neatly, we need to mark that gate IC number properly and decide which input is given to which pin of your different ICs and which output port will generate which intermediate result and all. mark all these input output port properly in this diagram, then it will be easy for you to connect any such complex logic circuit. It will generate the exact result without any mistake. Okay, so this is the diagram, and see here we need to make use 3 input AND gate. Here it is 4 input AND gate. Here it is 3 input OR gate. Okay, so in addition to our normal ICs, that 2 input AND, 2 input OR and NOT gate, we need to make use some more ICs here for implementing using that 3 input OR gate, 3 input AND gate and all. Okay, so this is the circuit. And one more situation we can consider here, that is, here we are using 3 input OR gate for generating the carry out part, and before that here we need this, anyways we need this 4 input OR gate for generating this sum part. Okay, so we can make use the same 4 input OR gate in order to generate the carry also. How this possible? We can make use that 4 input OR gate and connect these 3. Okay, connect these 3 input as it is, like this, BC, AC and AB output as an input, and short any one of these and connect as the 4th input. Then it will generate the exact result as that of this 3 input OR gate. That means we can make use the same 4 input OR gate in order to generate the carry out part. Otherwise, we can make use one 4 input OR gate IC, another 3 input OR gate IC, and we can generate separately sum and carry. The other option, we can make use the same 4 input OR IC, 4 input OR IC, and we can generate the sum, and this one also we can generate using the same IC. For that, we can short any one of this input and connect as the 4th one to this particular IC. Okay, so this is about full adder circuit implementation. And this is a half subtractor circuit. This is for subtraction. This is exactly like our half adder circuit. 2 input and it will generate the difference value as the result and borrow. What's the meaning? Here it is 0 minus 0. 0 minus 0 is 0. This subtraction is directly possible without taking any borrow from the next level. So, difference is 0 and borrow is 0. Okay, next is subtraction 0 minus 1. Is it easy or is it directly possible to do this subtraction 0 minus 1? Means 1 is subtracting from a small value 0. Is this directly possible? No. In order to perform this subtraction, we need to borrow from our next higher level. So from here we need to borrow 1. That 1, here it become 2. Before that, we can consider one decimal subtraction. Suppose this is 3 minus 4. Okay, for subtracting 4 from 3 in our decimal system, this is not directly possible. We will take one borrow from our next level. We will take one from its 10th level. So, here it become 10. Right? So, 10 plus 3, 13. Now, after borrowing from the next level, we will subtract this 4 from 3 plus 10, 13. 13 minus 4. It is 9 then. Okay. This 3 is actually taking a borrow from its 10th position. That is why this borrow become 10 here, because this is decimal system. right? So 10 plus 3 is 13. Now 13 minus 4, it is 9. Similarly, in this binary system, 0 minus 1. 0 minus 1 is not directly possible. We need to take some borrow. This is binary system, okay? So we need to take some borrow from the next level. Okay, so that 1 here it become 2. That value become 2. The 2 in decimal is actually 1 0. Sorry, 2 in binary is actually 1 0. Okay, that value is actually equal to 2. Then 2 minus 1 is 1. How can we write that value 1 in binary? It is equal to 0 1. Okay, so this is the subtraction result. Here, in order to perform this subtraction, we can, here it is 0, so we can consider this least one only. Okay, here in order to perform such subtraction, we need to consider one borrow from the next level. So this case, the difference is 1 and the borrow is 1. Okay, and here it is 1 minus 0. No confusion, because this is a direct subtraction. 1 is large value and 0 is small. 1 minus 0 is 1 only, without any borrow from the next level. And next 1 minus 1. 1 minus 1. There is no case of borrowing from the next level. 1 minus 1 is 0. With borrow 0. In this particular case only, it will consider that borrowing from the next level. So here, that value we need to consider. The borrowed value 1 become 2 here. Then 2 plus 0 is 2. Then we need to subtract this 1 from that 2. 2 minus 1 is 1. That 1 in binary is 1 itself. So that is the difference equal to 1 and the borrow from next difference equal to 1 and borrow from the next level is 1. Okay, so for this we can generate that expression. Here it is. The expression is a bar b or ab bar, which is a XOR b, which is exactly like the sum part of our half adder circuit. And what about this borrow? Borrow, it is a bar b. Okay, so this is that simplest circuit implementation for our half subtractor a XOR b and a bar b, if this XOR gate is available. And suppose the question is for implementing the circuit without using this XOR gate, and you are provided with only those basic gates. In that case, the circuit is this one. This is exactly like our half adder circuit. The only one difference is this borrow part. Here the carry part is AB. Here it is A bar B. So after implementing this half adder circuit, we can keep this sum part as it is here, because sum part of half adder and the difference part of half subtractor is the same. It is A XOR B. Okay, and we can change this carry part with borrow, and we can directly implement that half subtractor from this half adder in your lab experiment. Okay, in order to connect A with this AND gate, we can connect that A bar with the AND input. Then it will convert it to half subtractor. Okay, so before implementing all this circuit, always practice to write the IC number properly in this diagram and mark this input output port connectivities. For that, we need to refer that IC pin diagram. Okay, thank you.